Welcome back, students. In this video segment, we begin the final chapter of our semester, Infinite Sequences and Series. In section 11.1, we're going to give you a brief introduction to the concept of a sequence, but I thought I'd give you in this section an introduction to both sequences and series. So I'm going to start with an example. And the example is my own, so this example is not in our textbook. So for this example, let's assume that we're in a restaurant and the players in our mini play here are a waiter and two people on a date. Okay, so as usual, forgive my drawings. I'm going to draw these people, but it's mostly for effect, so we really don't need the drawing, but I'm going to do it anyway. So here's our waiter. Waiter is going to be a square-bodied person. And what we're going to do is observe what's going on from the point of view of all three of these people, the waiter and the two people on a date. So here's our next player, one of the two people on a date, really hungry guy. How do I know he's hungry? Well, he's real skinny. It looks like he hasn't eaten in a long time. And his date. Here she is, wearing a nice dress. And again, the point of view of this problem is from the three individual people. So here's what happens. It's a pizza restaurant. So the waiter, from the waiter's point of view, all he gets to see is a list of what's in their orders. And let's assume that they decide to go Dutch. That means they're gonna order separate checks. Okay, so here's the check for the guy, and here's the check for the girl, and both the guy and the girl are going to order an entire pizza for themselves. So, from the point of view of the people on the date, we get to see only what's in their stomachs, at least what they've ordered from the restaurant in their stomachs. Okay, so the waiter orders for the guy, takes note that he's ordered one pizza, she's ordered one pizza, and into their stomachs each go one pizza. So from all 3 points of view, it looks like there's really not that big of a difference. 1, 1, 1, and 1. Okay, so let's continue on. The two people on a date, they eat their pizza and they both decide that they're still hungry, so they're going to order some more. But they're not as hungry as they were when they walked into the restaurant. So each of them orders a smaller order than their previous order. In fact, each of them orders a half a pizza. So the waiter takes note that the guy has ordered a half a pizza, and the girl's ordered half a pizza, and popping into their stomachs another half a piece of pizza. Well, this time we add the pizzas, or the portions of pizzas, to what's in the contents of their stomach already, the previous pizza they ordered. So the waiter is just making a list of what they've ordered, and what we get to see from the people on the date is the total of what's in their stomach. So once again, they've each eaten their additional half a pizza, and they decided that they're still hungry, so they're going to order more pizza. In fact, this is going to continue on for the rest of time. These people are not leaving this restaurant. They're just going to be making more and more and more orders. The waiter never gets to go home. He has to make these lists, these separate lists, these checks for these people. We're going to do this forever. Well, okay, so the guy on a date orders a half of his previous order. So he decides that he's going to order a fourth of a pizza. Okay, so pop that into his stomach. So we add to the previous amounts a fourth. She's going to order a different amount. She's going to order 1/3 of a pizza and then eat that. For the next order, the guy on the date decides he's going to order half of his previous order again. So he's going to order 1/2 of 1/4 or 1/8 of a pizza, then eat that. She's going to order 1/4 of a pizza and eat that. So there's a pattern going on here. For the guy on the date, his subsequent order, his next order is always 1/2 of his previous order. So he orders next 1/2 times 1/8, 1/2 of 1/8, which is 1/16. What she does is she increases the denominator of the fraction of her previous order by 1. So she's ordering 1/5 of a pizza. Pop those into their stomachs. 1/5. And as I mentioned a couple minutes ago, this procedure is going to go on forever. The waiter is just going to keep noting what the two patrons are ordering and continue these individual checks forever. And the people on a date are just going to continue to eat these pizzas, or eat these orders. Okay. Now, the reason for this example is that it's bringing up both the things that are talked about in this chapter. Remember, just above there, I've written out that we're talking about infinite sequences and infinite series. A sequence is nothing more than a list of numbers. It has to be an infinitely long list of numbers, an infinitely long list of numbers in a particular order, so it's in a definite order. A series you get by adding up the terms in the sequence. So the sequence is just a list of numbers, infinitely long list, and a series is the sum of those things in the list. So the sum of the elements of a sequence give you a series. And I'm taking this valuable time to talk so much about it because it's the first problem that students have with these two topics, is interchanging the ideas. A sequence is just a list. A series you get by adding up the terms in that list. Okay. I want to look a little more deeply at these sequences and series. So I'm gonna write out here in red that what we have are sequences, two sequences from the point of view of the waiter, and from the points of view of the two patrons, we have what are called series. Okay, central to the topic of sequences and series is the idea of convergence. Just like when we studied improper integrals, certain improper integrals converged. They equaled or they approached a particular number, and certain improper integrals diverged. Well, we have the same type of thing going on with sequences and series, the ideas of convergence and divergence. In fact, the concept of convergence is the central topic for all of chapter 11. And it's a very difficult topic to approach. So this is partially why this chapter is the most difficult chapter in the entire course, is that the concept of convergence is very, very difficult to get a handle on. So we're gonna unpeel that onion, the onion of convergence versus divergence, as we go through the chapter. But for now, I wanna concentrate on just the difference between a sequence and a series. Sequence is a list of numbers in a particular order. We don't for the guy on the date, his list. We don't list 1/4 first, and then 1/8 seconds, and then 1/3, and so forth. We list the orders in the order that he gave the waiter. Okay, so a little introduction to the concept of convergence. So notice that from the waiter's point of view, when we look at his checks, the individual sequences, the slices of pizza that are being ordered are getting very small. In fact, the slices of pizza in both orders are approaching 0 in size. So both of those sequences are said to converge. Both of those sequences converge. In fact, they converge to 0. So if the elements, the individual numbers in a sequence, approach 0 as we look at more and more of those numbers, the sequence is said to converge to 0. Okay, and I'm not writing this out because it's mostly an introduction. We're gonna unpeel this very, very slowly, starting in a few minutes. Now, the thing with here's the thing with the two people on a date. One of them's going to die. It's going to take a very long time for that person to die, but one of the people on the date is going to end up eating an infinite amount of pizza as time goes on. One of them, on the other hand, lives, and in fact, the amount of pizza in that person's stomach approaches two pizzas. Okay, so the who lives, who dies. That's the main question in this chapter. Although we're not gonna look at such gross examples of tying series and sequences to life and death, but this one really gets the job done in terms of understanding of what's going on. The series 1 plus 1/2 plus 1/2 of 1/2, 1/4 plus 1/2 of 1/4, 1/8. That is the series that represents the amount of pizza and the male on the date, the guy on the date. This series converges to 2. This series converges to 2. This is a very, very important series. This is an extremely important series, and we're going to spend some quality time on it on our next lesson, discussing this series. What this means in terms of the terminology the series converges to 2 is that as we keep adding more and more and more pizza to this guy's stomach, but we have to add the pizza according to the sequence of his order, that the series is what you get by adding together the elements of a sequence. This series gets closer and closer and closer and closer and closer and closer and closer to 2. The more pizza he eats, the closer the amount of pizza in his stomach gets to 2. Okay, so this series is said to converge to 2. On the other hand, I think I kind of gave away who's going to be living and dying here. Her sequence, the girl on the date, her sequence her series. I've already done the most common mistake. I've called a series a sequence. This is a series. Her series, the amount of pizza in her stomach. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc., etc., etc. This series diverges. This series diverges. In other words, the amount of pizza in her stomach becomes infinite. It's impossible to tell just by looking at these two series, however, unless you have some really powerful knowledge of series, and you're going to gain that knowledge, it's impossible to tell which of the two series converge and which of the two series diverges. Even if we could tell that the first series converged, it's kind of hidden how the idea of how it converges to 2. Okay, so in this chapter, we mainly examine whether a series converges or diverges. Towards the end of the chapter, and which will bring us to the end of the course, we're going to be interested very much in determining the value to which a convergent series converges. Okay, so let's before we dig into the nitty-gritty of this section, let's complete the concept of convergence of series and sequence by looking at the individual orders. The guy's check, the check from the guy on the date, his sequence looks like 1, 1/2, 1/4, 1/8, 1/16. Just rewriting it again. This sequence converges to 0. This sequence converges to 0. Remember, in a sequence, we don't add up the terms. To 0. We just look at the size of the terms as we add more. We insert more and more terms into the sequence, and each of the slices of pizza are getting infinitely small as we move on. The sequence representing the female on the date. I guess I could have given them names instead of calling them male and female. Her sequence also converges to 0. This sequence also converges to 0. So this sequence converges to 0. The slices of pizza that she's ordering are becoming infinitely small. The slices of pizza that the guy is ordering are getting small fast enough so that throughout all time, the amount of food in his stomach will approach 2. Her slices of pizza are not converging to 0 quickly enough. It turns out that throughout all time there will be, and the amount of pizza in her stomach will become infinite. Interesting to note about her series, though, what's going on in her stomach, that her series diverges. The amount of pizza in her stomach becomes infinite, but very, 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 very slowly. It will take, if they order pieces of pizza, let's say 10 minutes apart from each order, it will take her many, many centuries before she'll even start to notice the amount of her stomach that she's getting really, really, really full. Okay, all right. So in this section, we primarily talk about, in fact, all of 11.1 is dedicated to a discussion of not series. That's for most of the rest of the chapter after 11.1, but to sequences. So let's talk about sequences. Let's talk about sequences, the idea of convergence, and some notation, and so forth. Okay. So let's take a look at different possible ways of writing out sequences, of denoting sequences. So notation. So our discussion from now to the end of this video segment is going to involve, and I did it again. It's very easy to fall into the trap of interchanging the concepts of sequences and series, denoting sequences. Sequences are lists of numbers, infinite lists of numbers, and the list have to be in a particular order. Okay, so let's consider the sequence 1, 1/2, 1/4, 1/8, etc. Sequence that represents the check, the check that the waiter, the orders that the waiter took from the guy on the date. Okay, so one way to list a sequence is to list them the way the waiter in the restaurant saw them, as a list, using braces to enclose the terms in the sequence, and a ... after writing out a few terms in the sequence. How many terms in a sequence that are listed is not determined. You can write out 3 terms in a sequence, 4 terms in a sequence, however many terms in a sequence is necessary so that the reader can get an idea of what's going on in the sequence, what the sort of formula for the terms in the sequence are. You could also list or give the formula for the terms in the sequence. And one way to do that is to give a function which tells you the particular term in the sequence that you're referring to. So for example, let's take a look at the sequence again. 1 is the first term. So this is the first term. 2 is the second term, and so on and so on and so on. So I'd like to create a function which gives me the nth term in a sequence, period, the nth term in a sequence. Okay, so what I'm going to input into this function is the particular term that I'm looking for. So if I want, for example, to designate the first term, I would say A is the function that represents the term in the sequence. So A sub 1 for A sub the first term is 1. A sub 2 is the 2 in the subscripts indicates that we're looking at the second term, is 1/2. A sub 3 is 1/4, etc., etc., etc. So another way of denoting the sequence, the entire sequence, is not to list the individual terms a sub 1, a sub 2, a sub 3, but to list a function, or to write a function that gives you the nth term in the sequence. This is called the general term of the sequence, the general term of the sequence. Write that out. Term sequence. So the general term of the sequence, and this is a skill that really takes some developing to get good at. If you're given a list of the terms in a sequence to come up with a function, the general term of a sequence, that's not always easy. But here it's not so bad. It looks like 1/2 should be involved, because I need to multiply my previous order, if these were considered orders of pizza, by 1/2 to get my next order. So it should involve 1/2 being multiplied by itself. 1/2 times 1/2 to get the next term, multiplied by 1/2 to get the next term after that, multiplied by 1/2. So it looks like repeated multiplication of 1/2. But 1/2 to the what? Well, the first term has 1, and 1/2 to the 0 is 1. The second term is 1/2 to the 1. The third term is 1/2 squared, sorry. So it looks like the particular nth term in the sequence we get by taking 1/2 and raising that to the n minus first power. Okay, so this is another way of identifying or denoting the sequence. The first way, just list the terms in the sequence. The second way, write out a function using subscripts for the general term in the sequence. Another way of doing that is to kind of combine the first two ways and take the general term and put it inside braces. Kind of did a little algebraic simplification there without telling you about it. This is 1/2 to the n minus 1. So putting the general term within braces, the last way, and this one's not as popular, is to use that the way I just did, combination of the braces set notation plus the general term, and then writing as in superscript n equals 1 and infinity. This way is arguably the best way to write out the sequence, because it tells us where to start n for the sequence. The general term for most of our work in this chapter, we assume that n starts at 0 or 1, but our knowing where that starts is based on putting ourselves conceptually in the problem. So if I wanted the general term to start, let's say in the fourth order of pizza at the 1/8, then I would need to state that n started at 4, because 4 minus 1 would be 3, and 1/2 to the third would be 1/8. So the last way of denoting sequences is arguably the best, because it tells us where to start the sequence. Since sequences always involve an infinite list, the writing of the infinity in the superscript in that last notation seems kind of silly, because it's always infinity. Okay. The most popular way of designating sequences is simply by listing the general term, listing whether in brace notation or just as a function, a sub n. The most common letters used for denoting sequences are small letters, but capital letters are allowable. In mathematics, any symbol can be used to represent any quantity. Just depending on what the author's preference is for symbols and so forth. So just to get this idea ingrained, generally we can write the terms in the sequence out: a sub 1, a sub 2, a sub 3, dot dot dot. Or we can write a sub n, a function of n with the variable in the subscript, or we can plop that function into braces, or we can plop that function a sub n, the general term, in braces, and indicate where the sequence starts. Okay, and always to infinity. Okay, so how do we visualize sequences? That's an important point or an aspect of chapter 11, and it's another point that makes chapter 11 the roughest stuff in the course. Is we actually have to start seeing numbers, visualizing numbers. And I don't mean by, for example, visualizing 1/2 by looking at the fraction 1/2. I mean actually visualizing the behavior of sequences and series with our eyes, and not looking at them so much as numbers, but somehow visualizing them graphically. And there are a couple ways of doing that. So let's talk about visualizing sequences. Visualizing sequences. One way is to put the terms in the sequence on a number line. So here's a number line, and let's suppose we want to look at the sequence a sub n equals 1 over 2 to the n minus 1. Okay, so if this is 0 and this is 1 on the number line, we could indicate the first term in the sequence. Remember, the actual sequence, if we write out, looks like 1, then 1/2, then 1/4, then 1/8, etc., etc., etc. We put a heavy dot at 1. There's a sub 1. Then we put a heavy dot at 1/2. There's 1/2. Then we put a heavy dot at 1/4. Then a heavy dot at the next term, 1/8. And we keep doing this. And you can physically see what's happening with the terms in the sequence. What I like to do, and it's not, I didn't make this up. I grabbed this probably from when I took calculus. What I like to do also is to indicate the kind of the behavior of the sequence terms in the sequence by drawing a little dotted line from each term to the next. So it's like a little bug is hopping toward the origin, and it's doing so in such a way that it cuts its distance in half to the origin at each step. So we go from 1, and the half of the distance from 0 to 1 is a half, then half of that is a fourth, and an eighth, and so forth. Okay. The important thing is that you're able to draw a diagram that makes sense to you, because as I mentioned, we're going to need to actually see with our eyes what's going on with numbers and sequences and series. Another way to do this is to do this in 2 dimensions, which is more what you're familiar with, because you've done a lot of graphing through calculus. To do this sort of thing in 2D. Okay, and by that I mean you can put the terms in the sequence vertically, and the value for n horizontally, and then graph the terms in the sequence as dots, but in two dimensions. So when n equals 0, in fact, I guess we're starting at n equals 1. So when n equals 1, I'm looking at 1. So when n equals 1, I'm looking at a value of 1. When n equals 2, I'm looking at a value of 1/2. When n equals 3, I'm looking at a sequence value of 1/4, etc. And this gives you a way to see what the terms in the sequence are doing. In fact, both of these let you give you an idea of that concept of convergence. If we draw them, whether we draw them in 1 dimensions on a number line or in 2 dimensions in the plane, we see that the terms in the sequence are becoming very, very small. As n increases, the terms in the sequence are approaching 0. And that's why we say that this sequence converges to 0. So let's go back to the concept of, or the notion of convergence. In fact, this is a very good time for that. Let's talk about convergence of a sequence. Remember, all of our discussion takes place with respect to sequences in this section, in section 11.1, as opposed to series adding up those terms in the sequence. Convergence of sequences. The previous sequence converges to 0. The sequence 1 over 2 to the n minus 1 converges to 0. To indicate that, we can write several things. We can write the limit as n approaches infinity of the general term 1 over 2 to the n minus 1 is 0. Okay, and that will do just nicely. And so let me give you an idea of separate ways of denoting this concept of convergence. It's not really convenient to be writing every time we talk about convergence, the limit as n approaches infinity of the general term equals whatever the sequence converges to. So it would be nice if we could streamline this notation. So we could also write, instead of writing the limit as n approaches infinity, is we could write simply that 1 over 2 to the n minus 1 arrow 0 means converges to 0 as n arrow approaches infinity, as n approaches infinity. Now even this has something in it that we don't have to write. It's not necessary for us to write, because the idea of convergence or divergence, it always depends on n approaching infinity. So the best way to denote the convergence of this sequence to 0 is simply to write 1 over 2 to the n minus 1 approaches 0. This is the best notation. And by best, every time we say something like best, it becomes an opinion. This is, in my opinion, this is the best notation. You can use any notation that we have above. I think this is the best because it's the shortest notation. So if you're thinking, well, 1 over 2 to the n minus 1 approaches 0 as what? Well, convergence or divergence happens only as n approaches infinity. So it's understood that n is approaching infinity. So just to summarize, generally, the concept of convergence. The sequence a sub n converges to L if the limit of a sub n as n approaches infinity equals L. The sequence, this notation can be simplified. We may simply write, we can simply learn how to spell simply. We may simply write, that's the first time I ever dotted a Y. No, it's probably not the first time. We may simply write a sub n arrow L to indicate this. So a sequence diverges if the limit as n approaches infinity of the general term does not exist. Okay, so the concept of convergence has to do with what's happening to the general term of a sequence as n becomes infinite. Okay, so let's take a look at a rather lengthy example. I want to consider different sequences, and I want to determine whether they converge or diverge. And what I get to use is all the limit properties that I learned in Calc 1. Your author summarizes this in section 11.1. He rewrites the limit theorems that you learned in Calc 1, but specifically for sequences. So, for example, determine whether the sequence converges or diverges. So determine whether the sequence converges or diverges. So here's our first sequence in this example. Let's take a look at the sequence whose general term is -1 to the n. All right. Well, if you can't tell just by looking at the general term whether a sequence converges or diverges, look at the numbers, look at the terms in the sequence in the different ways that we've looked at so far. You can write out the terms in the sequence. When n equals 1, we're looking at -1 to the first power, which is -1. When n equals 2, -1 squared is 1. When n equals 3, -1 cubed is -1. So it looks like the terms in our sequence alternate between -1 and +1. So if we're looking at the limit of the general term as n approaches infinity, the general term doesn't tend to approach one number. In Calculus 1, we state that the limit of that general term as a function then doesn't exist. Okay, so this sequence diverges. The sequence diverges. Something else is important is happening here. The general term is not approaching a single number, so that's enough for the sequence to diverge. And notice that the general term is not approaching infinity, so the idea that a sequence diverges is not connected necessarily to the terms approaching infinity, although that happens an awful lot in our course. But it's not necessary. So if a sequence diverges, that just means that the general term is not approaching a constant value. It doesn't mean that the terms in the sequence are becoming infinite. Okay. Now, if it's not enough for you to see that this sequence diverges by looking at a list of the sequence as a list, then draw the numbers on a number line, or use the other graphical technique I showed you. If this is 0, and this is 1, and this is -1, the terms in the sequence bounce back and forth between -1 and +1. So if you use that kind of dotted line to indicate what's going on, the sequence starts at -1, it goes to +1, then -1, to +1, -1, +1. All we do is bounce backwards and forwards between +1 and -1. So that's enough. That's enough for us to, at least for me, that would be enough for me to say that, hey, this sequence is not, the terms in the sequence are not approaching a single constant. So this sequence diverges. B. Let's take the sequence and let's do this. Let's take a look at the sequence -1 to the n minus 1 times 1 over 2 to the n minus 1. Okay, so what I've done is I've kind of combined the only two, well, two of the only two sequences we've looked at so far. In part A, we have that sequence that alternates between -1 and +1. So you notice that the general term in our sequence now has that alternating factor. I changed the exponent to n minus 1. All that does is it starts the alternating from +1 to -1 instead of -1 to +1. And I also multiplied that alternating term by the terms in the sequence for the original guy in a day. His orders of pizza were 1/2 of the previous order. So what's happening here? What's happening? Well, look at the terms in the sequence. Look at the sequence by listing the terms. When n equals 1, I get -1 to the 0, which is 1, and I get 1 over 2 to the 0, which is 1, so we get 1. When n equals 1, the -1 to the n minus 1 gives me -1. When n equals 2, I think I might have said 1. When n equals 2, I get -1 to the 2 minus 1, which is -1 to the 1, that's -1. And the 1/2 to the n minus 1 gives me 1/2. Next term is then positive 1/4, then -1/8, then positive 1/16. The terms are getting small. That is, they're approaching 0, but they're alternating between positive and negative. So this sequence also converges. In fact, it converges to 0. The sequence converges to 0. And again, you don't have to rely on looking at the list. You can look at the individual numbers to get an idea of what the sequence does. The first term in the sequence is 1. The second term in the sequence is -1/2. The third, so we bounce from 1 to -1/2, then to positive 1/4, then to -1/8, then to positive 1/16. So we go back and forth and back and forth and back and forth, bouncing across the origin, but getting closer and closer to the origin as n approaches infinity. So the sequence converges to 0. The most important part of this statement, though, is that it converges. To what the sequence converges, it's nice to note, but I'm only interested right now in whether the sequence actually converges or diverges. So the sequence converges, happens to converge to 0. Let's take a look at another one, C. So let's take a look at the sequence whose general term is n over n plus 1. Okay, so what is this sequence doing? Well, notice that the terms in the sequence are never equal to actually 1. We have a fraction where the denominator is always 1 more than the numerator, so the fraction will never equal 1. However, notice that the bigger n gets, the less significant that adding 1 in the denominator gets. So if n equals 1, I'm looking at 1/2. Okay, the adding 1 in the denominator does have a significant effect to the whole fraction. But look what happens when n equals 2. I have 2/3. N equals 3, 3/4. N equals 4, 4/5. That adding 1 in the denominator is becoming less and less significant to the numerator. That is, as n gets very, very large, the entire fraction is approaching 1. Look what happens when n equals 100. I have 100 over 101. That number is very close to 1. Look at what happens when n equals 1,000,000. When n equals 1,000,000, I have 1,000,000 over 1,000,000 and 1. Imagine having $1 million and somebody gives you an additional dollar. Is that additional dollar really significant to you? How much would you tell people that you had if somebody gave you a dollar, if you had $1 million already? You'd say, I have $1 million. So when you divide a large number, by that same large number plus 1 more, that number becomes closer and closer to 1. depending on how large the number is to start out with. So this sequence converges to 1. The sequence converges to 1. Converges to 1. Okay. I'm going to draw roughly what's going on the number line, because our next sequence is going to really kind of rely on understanding this particular sequence. When n was 1, I got a half. That's about right there. When n equals 2, I got 2/3. So let's say that's 2/3. N equals 3, I get 3/4. N equals 4, I get 4/5. N equals 5, I get 5/6. These numbers are not uniformly approaching 1 the way I have them doing it. But we notice that the terms are getting closer and closer and closer to 1. So they're bouncing closer and 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 closer. Okay, but coming in from the left, approaching 1 from the left. The reason why I drew out that last list of the members of the sequence on the number line is because it's going to help us. It's going to help us understand what's going on when I take the terms in that last sequence and multiply by the factor that makes my terms alternate. -1 to the n or -1 to the n minus 1. Either case, all that does is alternate between +1 and -1. So all I'm doing with the terms in this sequence are making them half of the terms negative and half of the terms positive. More specifically, I'm making the terms alternate between negative and positive. So specifically, when n equals 1, I have -1/2. N equals 2, I have +2/3, then -3/4, then +4/5, etc., etc., etc. Now, without that alternating term, without the -1 to the n, this sequence converged to 1. With that alternating term, though, we have a very different situation. Let's take a look at what happens if we graph the terms in the sequence on the number line. So the first term was -1/2, is -1/2. Then the next term bounces us up to +2/3. So we go from -1/2 to +2/3, then to -3/4, -3/4. Oh my goodness, it's turning out kind of ugly there. It bounces to -3/4, then +4/5, then -5/6, etc., etc. The terms are bouncing across the origin. Half of them are approaching 1, half of them approaching -1. So this sequence diverges, even though it looks like the sequence is converging to ±1, even though it looks like an infinite number of the terms are approaching or becoming infinitely close to 1, infinite number of them are approaching -1. Convergence relies on the sequence approaching a single number. So the sequence diverges. The sequence diverges. Okay. So let's take a look at our next sequence. Not all sequences have to be difficult. E. The sequence that contains the general term 3. So the first term is 3. The second term is 3. The third term is 3. The fourth term is 3. This sequence converges. This sequence converges. Sequence converges. In fact, what does it converge to? It converges to 3. For a sequence to converge, that means as n gets very large, a sub n needs to become arbitrarily close to, in this case, 3. A sub n equals 3. The limit of 3 is 3 as n approaches infinity. The limit of a constant is the value of the constant. So the sequence converges to 3. Okay, let's take a look at another one. Let's take take a look at the sequence whose general term is n over e to the n. Now we're getting a little difficult, now a little more difficult. It may not be clear by listing the terms in this sequence what the sequence is approaching. If you did that, you'd get, if n equals 1, you get 1 over e, n equals 2, you get 2 over e squared, n equals 3, you get 3 over e cubed. Both numerator and denominator are becoming infinite. That's the key here. Both numerator and denominator are becoming infinite. So that suggests L'Hopital's rule. L'Hopital's rule deals with the two indeterminate forms, infinity over infinity and 0 over 0. Now here's the deal. We can apply L'Hopital's rule to this. In fact, we're going to. But we can't apply L'Hopital's rule to it directly. You see, the terms in a sequence, if you graph them in 2 dimensions, are dots. If you were to graph the terms in this sequence in the xy plane, you'd be looking at literally a sequence of dots. 1 over e, 2 over e, 3 over e, 4 over e, 5 over e, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. And you can't take the derivative of a dot. So remember, the L'Hopital's rule requires that we take derivatives of functions. And if you're hoping to take the derivative of a function at a particular point, you're looking at geometrically finding the slope of the tangent line to the curve at that point. So if you're looking at taking the derivative of a function, you can't have a tangent line at a dot. So what we do is we get around that by putting the terms in the sequence on a function. We make them ride a particular function. We make them ride this green function that I'm drawing. The green function that I'm drawing contains the terms in the sequence as particular function values. So the green function, if a sub n is n over e to the n, then the function, the green function on which these terms lie, is the function f of x equals x over e to the x. Okay, so here's how we handle this. I want to evaluate the limit as n approaches infinity of n over e to the n. The value of that limit is the value of the convergence sequence if it converges, or tells us that the sequence diverges if that limit doesn't exist. So what I do is I replace the n's, all the n's, with x's. And it's assumed that x takes on values in the domain of the function x over e to the x. In this case, we just use all real numbers. So with this little step puts the dots on the green function. And since we're now on a function that is differentiable by replacing n with x, we use L'Hopital's rule. So there's a very ugly LH. Make it a little better. So we use L'Hopital's rule. At this point, L'Hopital's rule says we take the derivative of the numerator and the derivative of the denominator. Again, we can only do this since this is one of the two allowable forms for L'Hopital's rule, infinity over infinity in particular. And as x goes to infinity, 1 over e to the x approaches 0. So the bottom line is we can use L'Hopital's rule on our sequences. We need to put the terms in our sequence, the dots, on functions that we can differentiate. So we temporarily replace n with x and then take the limit. Okay, let's take a look at another sequence. So I don't think I stated what happens. So the sequence converges. I guess I should answer the questions. Sequence converges to 0, but it converges is what I'm interested in. Okay, another example. Let's take a look at the sequence that contains the cosine of pi n over n as the general term. Okay. This sequence, or at least the part of the sequence that's disturbing to a lot of students, the cosine of pi n, this term, or this expression cosine pi n, is very popular in studying sequences and series. It's not a very intimidating term. Cosine of pi n. Let's take a look at what cosine of pi n looks like numerically. In fact, let me move this over a little bit if my notepad will allow me to. Let's take a look at a small chart of just n versus cosine of pi n. If n is 1, I'm looking at the cosine of pi, which is -1. If n equals 2, I'm looking at the cosine of 2 pi, which is 1. If n equals 3, I'm looking at the cosine of 3 pi, which is -1. And this pattern continues. All the cosine of n pi represents is an expression that either equals 1 or -1, depending on whether n is even or odd. Now compare that with the terms in our first sequence. The first sequence in this example, -1 to the n minus 1. When n was 1, actually, I don't think it's quite exactly equal to the term in our first sequence. I'm going to remove the -1, if my pad will allow me to do that. I had a student show me how to do this efficiently, and it's not working. Here it is. Okay. So when n equals 1, I have -1 to the 1. N equals 2, I have -1 squared. N equals 3, I have -1 cubed. And -1 to the 4th, etc. They're the same thing. The term, the expression -1 to the n, one of the two expressions that illustrate a sequence that alternates between negative and positive, -1 to the n is nothing more than a simple way of designating the fancier cosine pi n. So -1 to the n is the same thing as cosine of pi n. So the general term in my sequence, cosine pi n over n, is nothing more than -1 to the n times 1 over n. And that general term is the general term of a sequence that approaches 0. If n equals 1, I'm looking at -1. N equals 2, I'm looking at +1/2. N equals 3, -1/3. +1/4 for n equals 4, etc., etc., etc. The terms are getting very small. They're bouncing across the origin on the number line, but they're approaching the origin. So this sequence converges to 0. Sequence converges to 0. Okay. Okay, our last sequence in this example is as rough as it gets. This is as tough as this chapter actually gets in terms of the algebra that's required to determine things like convergence or divergence. So as we go through this example, keep that in mind. That most of the problems in this chapter are not going to be this difficult, but they do occur. So here we go. Suppose I want to determine whether the sequence n factorial over n to the n converges or diverges. So just as a quick reminder, n with the exclamation point means n factorial. So this is n factorial. N factorial doesn't represent a loud n. It's not n. N factorial means, specifically, for example, if I'm looking at n equals 5, 5 factorial is 1 times 2 times 3 times 4 times 5. Times 4 times 5. Okay, or 120. So 4 factorial equals 1 times 2 times 3 times 4, or 24. 3 factorial equals 1 times 2 times 3. Get the idea? Or 3 times 2 times 1. The order in which you list the terms in the factors in the factorial is not important. 2 factorial is 1 times 2, or 2. 1 factorial is 1. And 0 factorial, what is 0 factorial equal to? The most common responses I get from students in terms of what 0 factorial should be, the most common response is 0. But it's actually 1, and it's 1 simply by definition. It's made equal to 1 so that stuff works out. Okay, and by stuff working out, stay tuned. We need 0 factorial to equal 1 so that our work with sequences and series can work out. And there's no such thing as things like 1/2 factorial, or -5 factorial, or 7.4 factorial. So the factorial is a function whose domain is a set of natural numbers. So 0, 1, 2, 3, 4, etc., etc., etc. Okay. Notice that as n gets large, n factorial also gets large. In fact, n factorial gets large quickly. Imagine looking at 100 factorial. That would be 1 times 2 times 3 times 4 times ... all the way up to 99 times 100. That number would be huge. Okay, so n factorial grows very, very quickly. In the denominator of our sequence, we also have a function that grows very quickly, n to the n. Imagine substituting n equals 100. We have in a denominator. In the denominator, we're looking at 100 to the 100th for n equals 100. That's 100 times 100 times 100 with 100 factors of 100. So that denominator, n to the n, also grows very, very, very quickly. The idea in this example, though, is to determine what happens as n approaches infinity to n factorial over n to the n. The numerator is becoming very large. The denominator is becoming large. But notice that there are the same number of factors in the numerator and denominator, regardless of whether n is 50 or 100 or 500 or whatever. But in the denominator, the factors always stay the same number. In the numerator for this particular fraction, we have 100, then we have 99 and 98. If we go backwards, 97, 96. In the denominator, the factors each remain as 100, so the denominator is substantially larger than the numerator. The big question is it substantially enough larger in the denominator? Is the denominator substantially enough larger than the numerator so that this fraction approaches a constant, either 0 or some constant? Okay, so to do this, I'm going to use a trick. I'm going to use a trick that involves something from Calculus 1 that you didn't use very often in Calculus 1. You didn't likely use very often in Calc 1. Okay, so here's how the trick goes. Let's take the general term, n factorial over n to the n, and let's write it out. Let's write out what it actually equals. The numerator equals 1 times 2 times 3 times 4 times all the way up to just before the last term would be n minus 1, and then times n. The denominator, on the other hand, looks like n times n times n times n times ... all the way up to the next to the last term will be n, the last term will be n. Okay, I'm going to split this fraction apart into the product of separate fractions. I'm going to write this one fraction as Let me insert a little more room here. Bear with me on this. I'm going to write this as, oh my goodness, I don't want a stray mark in here. Okay, I'm going to write this as 1 over n times 2 over n times 3 over n. I'm just writing the one simple fraction as the product of a bunch of individual fractions. Times dot 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 times, next to the last factor would be n minus 1 over n, the last factor n over n. Okay. Now I want to look at each of those factors from the right side, from the right-hand side, back down to 1 over n. I want to look to the right, the last number, n over n, all the way down to 1 over n. So look at n over n. n over n, that equals 1. n over n actually equals 1. Now the next to the last term, the term just next to it, to get that term, I kept n in the denominator, but I decreased the numerator by 1. I'm looking at n minus 1 over n. So the numerator is less than the denominator, so that term is less than 1. The term just before it would have n minus 2 over n. That's less than 1. In fact, each of the terms all the way down to the first term, 1 over, each of the factors all the way down to the first factor, 1 over n, those are going to be less than 1. All I'm doing to go backwards to the first factor is I'm making the numerator 1 less than it was before while keeping the denominator the same. So each of those fractions is less than 1. Okay, so what I'm going to do is I'm going to replace a whole bunch of those factors, specifically the one starting at 2 over n all the way up to n minus 1 over n. I'm going to replace those with 1. But if I replace those with 1, I'm changing the value of the general term. So I'm going to leave 1 over n alone, and then it doesn't change the value of the general term, but as soon as I replace 2 over n with 1, I've created something that's less than the original general term. And I'm going to do that with all of the factors between 2 over n and n minus 1 over n. n over n is 1. So I've left the first factor alone. I've left the last factor, 1, alone. So I've replaced the general term in my sequence with a very simple expression. I have the general term in my sequence, n factorial over n to the n, has to be less than 1 over n. Now, the original general term, n factorial over n to the n, that term is the general term is always positive. Remember, for n factorial and n to the n, I can only substitute whole numbers. Okay, so n factorial over n to the n lies between 0 and 1 over n. I'd like you to think about what part of calculus 1 I'm going to be using here. The limit of, as n approaches infinity, of 0 is 0. The limit as n approaches infinity of 1 over n is 0. And the general term of my sequence is captured in between those two. So the limit of n factorial over n to the n as n approaches infinity, the only possible value of that limit is 0. I have the general term of my sequence trapped between 0 and something that approaches 0. So the general term of my sequence is squeezed in between. There's your hint of what we're using from Calc 1, is squeezed between those two values. So it must approach that common value of 0. What did I use? This is called the squeeze theorem from Calc 1. Some instructors call it a sandwich theorem or squeeze theorem. So the sequence converges. It actually converges to 0. The important thing is the sequence converges. Okay, so just as a reminder, the squeeze theorem, I'm going to write the squeeze theorem for sequences. The squeeze theorem. If I have a sequence C sub n that lies between two sequences A sub n and B sub n, and A sub n approaches L and B sub n approaches L, then the sequence whose general term is C sub n must also converge to L. Okay. Okay, so this ends this section 11.1 of our last chapter for this semester, chapter 11, and I'm looking forward to talking with you all again soon.